Okay, let's add some more information about how to do the update regarding the motion model. So we are supposed to write the update function, and that consists of two parts. First, update all probabilities of all positions based on the action. That means as we have the grid world and we have all the possible hypotheses where we could be, and about each of them we have this information inside of one cell of this array, and that particular row, column and direction. So it would be in this case row 1, column 2 and direction 0, 1, 2, 3. So this is a belief we are here, the probability. The sum of all of these is 1, and each of the arrow has some probability. And we received the information that there was a request for the robot to make a step, or to turn left, or to turn right, one of these. And something happened. We don't know what happened, because maybe if the information to the robot was sent to make a step, then it made a step. Maybe it didn't make. We have this characteristic, the P3 is the probability that it makes a step. If the command was make a step, and P4, the probability that the robot has turned left if the command was turn left. And so the first part of this update function is to go through all of them and update all of them to a new situation after this action has happened or maybe not. And then the second part of it is to update the probabilities. It's props based on sensor readings. So these are the two parts, and we have discussed this part already using these Bayesian formulas. First, if the robot is here, or let's consider this position. We don't know where the robot is, but consider this position. Then we have a reading in the direction the robot is facing, in the direction to the right and in the direction to the left. But there was an action, go forward first, and that has to be processed first, update all the probabilities, and then update all the probabilities for the first sensor, and then update all the probabilities for the second sensor, and then, so it's actually 4 steps, right? And the first step we didn't discuss enough. So let's take some position that we are considering, a position here, and we would like to estimate the new probability that we are just there at that position, row, column and direction. And we know that the action was make a step. So then we need to look at two things. One is, what was the probability that the robot was at the position from where it could make this step? And if it was here, then its probability P3, it succeeded. So there was some, let's give this a P0, for instance. So then we take P0 times P3, and that is the probability that if we were here, we will be here if the action succeeded. But it's also possible that we were here and the action didn't succeed and we still stay here. So we need to add the, maybe let's call this P9. So it's P9 times 1 minus P3. It didn't succeed. So this is easy. So this is the new probability for this P9 in the new iteration, right? But that is not everything, because we need to consider some special situations. One special situation is that we are talking about a position where it's not possible to get. So this is a wall. And that's fine, because if it is a wall, the probability of this position is 0. So even if we multiply 0 times P3, we get 0. So it could not get here by making the step. It could only get here by staying there with the probability 1 minus P3. That's fine. But the other funny situation is the other way around. Let's consider this position. And there is a wall here. So we were somewhere, we don't know where we were before. And now we would like to calculate the probability that we are here. So consider two possible starting locations. One starting location is here, then one has the P0, and then P0 times P3 will appear here. That's fine, this part is okay. But then this one, if we were here, then what could have happened? If we succeeded, we would be in the wall, but we cannot be in a wall. So then we would stay here. And if we didn't succeed, we would stay here. So in that case, instead of 1 minus P3, we should really have here 1. Because if we were here, then if we were given the direction, make a step, then we would stay here with 100% probability. So we just then add the P9 there. But it's not that good because, well, that would be a way to do it, right? It would be a sort of correct solution, but we have some additional information which can help us make it even better. And that additional information is that in the simulator where we are controlling the robot in the grid world, we know that the robot really is somewhere. And if there is a wall and the robot is located in front of the wall, and we tell step, we click on the step button, then nothing happens. It doesn't give the robot the instruction because it sees, oh, there is a wall, I cannot go there. So it doesn't even give the robot that instruction. And that's why we know that in this case, if we are considering the probability that we are here, then we can exclude those cases that we were here and we received the instruction go for one step forward, because that could not have happened because the browser JavaScript application doesn't allow it. So in these cases, when there is a wall in front of us, pressing the step button has no action, and therefore our update function will not even be called. And that means it will never happen that the robot could have been on this position and it received the step instruction. And so when we are calculating the probability of this position after a step instruction, then we are sure it was here. And it could get here with the probability P0 times P3. And the second term of this formula will be 0 in that case. For usual situations, yes, there is a chance that the robot was here. If there was no wall in front of it, right? Then it was allowed to press the step button. And in that case, yes, there is a chance that it will stay there with probability 1 minus P3. But in these situations, there is no chance it was here, and only this part of the formula will be used. But this causes a small problem. The problem is that this probability that was here, the P9, gets lost. The outcome is that when we sum, after we do update for all the positions, and we sum the resulting probabilities, we will not get 1, and we should. Because all those that are in front of the wall these P9s will get lost. The whole P9 is lost. And therefore we need to collect it. We collect all those P9s which are in front of the wall and distribute it somehow. And now you can have different proposals. One that I used and that worked was to distribute all these collected probabilities. So do an update, collect all those P9s, and then you have some chunk of probability, maybe 5% altogether, maybe 20% altogether, doesn't matter. And then you distribute this to all the rest, and you distribute it proportionally to that calculated probability. So everybody will get the amount of its probability, of its resulting probability proportionally, right? So if you would have, for instance, three different, only three cells in the whole cell would have a non-zero probability. One would be maybe 0.2, one would be 0.3, one is 0.1. They sum all to 6. So this one will get 2/6 of that. This one will get 1/2 of that extra probability that needs to be distributed, and this one it will get 1/6 of that probability. Okay, so this was the interesting part, that there are some special situations that need to be handled in addition to this simple update formula. This is what I wanted to share with you. Thank you.